Okay, so the next topic we're going to discuss will be torsion. So I'll go through the slides again because I don't have any markers with me. And next lecture I will go through them basically in this slides. Or I'll repeat myself because the issue I've seen in this, especially this topic in the beginning, it relies a lot on derivations because we just have to develop the equations similar that we did with the stress equations. So we'll go through the stresses, the strains, and come up with a set of equations at the end. And based on that, we can draw some conclusion out of it. So in the beginning of this lectures regarding torsion, so this lecture and next lecture will be a lot of based on just derivation. So it might go too fast if we follow on the lecture slides only. But for today, we are basically we don't have any other choice. So next lecture, I will go through it again just to be on the safe side. So with that said, is together with bending, torsion and shear will basically complete our lecture series for the three main topics for this lectures series and this class. And because similar to bending, we can always superposition a force acting on a structure in either a bending moment, a torsional moment, or a shear force. And based on that, if we know what the stresses is due to bending, torsion, and shear, we can basically have a complex loading condition. We can simplify it into the three basics and then analyze our structure in a simple way. So one thing what we can assume from now onwards on this topic, so we can always assume a pure torsional moment. And torsion is nothing else than an in-plane moment also. So what we do is we're going to look at a certain cross section. In this case, we're going to assume a solid beam for now, and then we're going to go to a thin wall structure later. And we're going to assume it's in pure torsional moment. So when we assume it's pure torsion, so like our positive points are defined as in this figure. So basically right-hand rule on the Z. And with that assumption comes along that we have no direct stresses. So we have no sigma x, sigma y, and sigma z's. And the shear stress in the xy plane is also equal to 0. So tau xy is equal to 0. And in addition, we have no constraints at the end of the rod. So it basically, the rods can basically move freely and warp is not a word just for displace out of plane. So often when we also discuss, like when we have warping, we're talking about displacement out of plane, and when we just mentioned displacement is often just displacements in the plane. So with that in mind, let's basically draw a grid on it and imagine to ourselves what would happen to the grid if we place down a torsion. So basically you can think of it as a tube and you twist on the both sides. So what we'll see is that a couple of things happens. So we're going to look at two segments. We're going to look at line AA and BB. So line AA is basically going, say, through in the XY plane, and then BB going from more through the thickness or parallel to the curvature of the bar. So we know that lines AA remain parallel. So those lines do not twist. And lines BB, if you can look, that's basically from this point. So any parallel line with the z-axis, which will happen is that will basically twist. It will go along with the curvature of the twisting. So those two observations are key to our starting point of our derivations. Okay. So that's slide 3 there. So with that in mind, we look back into our equilibrium equations for stresses. I think this was one of the first lectures we basically came to this equation set, and it's basically based on a cuboid that we draw all the stresses and we take the equilibriums in x, y, and z, and we figure out what was which terms canceled when which terms remained. So x, y, and z are body forces per unit volume, so acting on a body. Again, because we assume that we have a pure torsion, we also automatically assume there's no body forces acting on it, so basically those equal to 0. In addition, we also assume that stresses and sigma x, sigma y, and sigma z are equal to 0. So basically, partial derivative of sigma x with respect to x is equal to 0. Partial sigma derivative of stresses and y with y is equal to 0, and the partial derivative of the stresses in z with z is equal to 0. And in addition, we also said tau xy is equal to 0. So basically, in this equation, we can say knock out this one, sigma x, tau xy, sigma y, and sigma z out of it, and x, y, and z as well. And if we do that, we basically remain with three equations stating that tau xy with respect to z is equal to 0, and tau yz, or the derivative of tau yz with respect to z is equal to 0. And in addition, we know that the derivative of tau xz with respect to x plus the derivative of tau yz with respect to y is equal to 0 as well. So basically, for a pure torsion case, our basically three stress equation reduced to a slightly simpler format that we can say that we have tau xz with respect to z is equal to 0, tau yz with respect to z is equal to 0, and the partial derivative of tau xz with x and plus tau yz with y equal to 0. So we can do, so based on these three equations, we can already deduce some information out of it. So if we have an equation that would the function, and if we have an equation and the derivative with z is equal to 0, that means that the equation is a function of only the variables that are all except z. Because if you have the function of, say, if tau x z is a function of z, and you take the derivative, then you have a non-zero value. So because of that, we can say from the first equation that, or for the first two equations actually, we can say that tau xz and tau yz must be a function that is only a function of x and y and not z. Else the derivative with respect to z is a non-zero value. So that's very useful for us. And the third equation, similar to our compatibility equation, gives us a relationship between these two unknown stresses. Because again, we have tau xz here and tau yz here, and we already know this from our first two equations that these two must be a function of x and y, but they also must have a certain relationship between it, because if these two are a function of x and y, and here we take the derivative of x plus the plus something with the derivative with respect to y is equal to 0, there must be some relationship between these two functions that ensures that this equation is valid. So this is basically our compatibility equation in this case. Else we could have certain functions that satisfy the first two equations, but that do not satisfy the third equation. So now the question becomes, okay, what does this relationship look like, and how can we solve for that? Similar to the area stress function, what we're going to do, we're going to assume a certain function, and we're going to set some relationships for this function to be true. Just if you remember correctly, with the area stress function, we said we have phi, and the second order derivative of phi with respect to y is equal to our sigma x stresses. In this case, we again take a function phi. This time we call the Prandtl stress function, named after the first guy who came up with it, Prandtl. And we say that tau xz is our derivative of our function phi with respect to y, and tau yz is our function with respect to x, or the negative of the function phi with respect to x. So what we can do is we substitute that back to our third equation, where we have our tau x z with respect to x plus the partial derivative of tau yz with respect to y is equal to 0. If you plug that in, we see that we get the second order derivative of phi with respect to x and y minus the second order derivative of phi with respect to x and y again is equal to 0. So similar to our area stress function, if we choose a function that has this characteristics, so if our tau xz is defined by phi, the partial derivative of phi with respect to y, and if our tau yz is defined by the negative of the function phi with respect to x, then our compatibility equation that gives us the relationship between tau x z and tau yz is automatically satisfied. So as long as this condition here is true, then any function of phi will satisfy our compatibility equation, and we can get a solution out of it that's fully satisfies everything. So now, of course, the question becomes is how do we select an appropriate phi, which is function of the cross-sectional area of the shapes, and this is basically the trick that we have to figure out. So with basically trace, I basically mentioned that this was similar to our compatibility equation, but we still have our true compatibility equations that are still must be satisfied. So we have three stress equations that are satisfied in this manner, and now we basically have to look at the six compatibility equations that we had earlier, and to ensure that those are satisfied as well, so we get also the certification that we satisfy the displacement fields. And in addition to that, similar to the area stress function, we also, if we have boundary conditions, we must satisfy those simultaneously as well. So we get basically the same thing as what we had for the area stress function, but then applied to torsion. And to do so, we can look back to our compatibility equation, our stresses and strains. And if we look at back our strains, for example, we know that strain in x is defined by displacement in u over partial x. And similarly, strains in y is dv dy, and strains in z is equal to dw or partial w over partial z. And our shear stresses are defined by a function of u dy and v dx, etc. So, for example, gamma yz is partial v over partial z plus partial w over partial y. So what do we know more? We know we have our relationship from Hooke's law that gives us a relationship between stress and strain. And if we look at our generalized Hooke's law without the components of what's that called? Temperature involved, because normally you would have a delta plus alpha delta t here, so we ignore temperature effects. This is the strain terms that we have. So similarly, what we done before, we said we have a pure torsion case, so we don't have any direct stresses, so we can probably ignore terms like sigma x, sigma y, and sigma z. And we also don't have tau xy. That was also another condition that we had started off with. Let me see. Yeah, shear stress in tau in the xy plane is equal to 0. So we can plug in those conditions that we had into our compatibility equations, and we can see what we get out of those. Doing so, we can basically immediately get that the strain in x, y, and z must be equal to 0. The shear strain in x, y must be equal to 0, and the shear strain in xz and yz is equal to the shear stress in xz and yz respectively, divided by the shear modulus g. And now comes the fun part. So now we go basically into the derivation steps. So similarly, what we said before is by looking at the function, and I have to go back. Yeah, we said that tau xz, for example, here we said that tau xz with partial z is equal to 0, therefore it's only a function of x and y. We can make similar statements about the strains as well. Just because x, the strain in x is equal to 0 doesn't mean that we cannot use it. So basically, from the strain equal to x and the strain in z equal to 0, we can say something about the function u. So yes, if we look at the strains equal to 0, but the displacement u does not mean automatically 0. It just means that the displacement u is a function of y and z only, because you need to satisfy the condition that if you take the partial of the u with respect to x, it equals to 0. In a similar manner, we can also state that because our strains in z is equal to 0, our displacement function of w is a function of only x and y in order to satisfy that partial w partial z is equal to 0. And then from our Prandtl stress equations, we know that partial tau xc over partial z is equal to 0, and we know that the partial that the stress and the strain are basically related to each other. The shear stress and the shear strain are related to G. So we can say that if tau xc over partial z is equal to 0, then our shear strain of gamma xz over delta z must also be equal to 0, because shear modulus is always a non-zero quantity. So with that given, we get that partial gamma xz over partial z is equal to second derivative of u with respect to partial z, and the second partial derivative of w with respect to x and z. So what we did here in this last step is, let's see, so what's it again? Xz. So we take xz here and we plug it into this equation here. So we get gamma xz over partial z. So this becomes partial u squared over partial z squared plus partial w over partial x partial z. And again, from our strains in z, since those are equal to 0, we know that our function of w is a function of only x and y, and therefore we can conclude, if this is only a function of x and y, w, that if you take the partial derivative, second order partial derivative of w with respect to x and with respect to z, then there would always be 0, because w cannot be a function of z. So if you take the derivative of a function of something that's not has a function that's not a pair, it's always 0. So going pretty fast through it, I understand. So that's the reason I'll repeat this in the next lecture a bit again, because probably would have taken us like more than a half hour to get this point if I have written it out. So from basically the last statement that we know, we can come up with the fact that since this must be true, then we can say a similar story about the u displacement, and we're going to use the u displacement as a function as an example here. Then we know that if u is a function of y and z, then we can state the function u as u times z times function f1, that's a function of y, plus function f2, that's just dependent on y. So now we have basically our displacements. We have a method to describe our displacement in u. So we said that it's basically a function. U is z times a function 1 plus a function 2, and the two functions are dependent on y only. So another thing that we assumed in the beginning, we said it warps, and we didn't have any shear stresses in plane X and XY. So therefore, the warping occurs out of plane. So basically, if we torque something, we get displacement out of plane, not in plane. Because of that, we can basically plug in if u is equal to 0 or z is equal to 0, say an end of the rod, then the displacement in u must be equal to 0. So this goes back to the first figure that we see here. So if we now look at, say, if this is z0, if we put a torsion on it, we get some out of plane displacement, but in plane displacements are basically remain the same. So those are equal to 0. So because of that is we know that at z is equal to 0, u must be equal to 0. And if we plug in this into the first equation that we have, automatically means that our second function that's dependent on y only must be equal to 0. So our function of u, or displacement u, is now currently a function of z, z multiplied times a function f1 is dependent on y only. So we can apply the same procedure basically to w, and we just picking up two different strains and the same tau xy and tau yz. So we can come up with the same thing for v, and we can also say that v is a function of z, but multiplied by a different function that's dependent on y. And together again, if we use our third assumption that we said basically no shear stresses in xy plane. So this in addition to our assumption that we didn't have any direct stresses, that sigma x, sigma y, sigma z is equal to 0, and tau xy is equal to 0. If this must be true, then we also have no shear strains. And if we have no shear strains, then the partial u over partial y plus partial v over partial x must be equal to 0. Because of that, we can come up with we can define a function that combining these two together, we know that partial u of partial y is equal to the basically partial f1, which is function of y over y is equal to a constant c1. And similarly, for this to be true, we can derive this. We would get this the same thing. We get basically a c2, but in order to comply with this requirement here, then these two coefficients must be equal and opposite in sign. And that's basically to comply with this condition that if we have no shear stresses, therefore no shear strains, and of course G can never be 0, so therefore this condition must apply. And then we can basically say, so what we can do is then write this C1 as just a constant vector k, and we say that these two must be equal to each other. So therefore our displacements now in u and v have the form of the constant k multiplied by y multiplied by z. And the v displacement is the negative of k multiplied by z and y. And then we can go to our shear strains that were non-zero, that were the xz and the yz components. We start with the shear stresses not equal to 0. Since the shear stress is not equal to 0, that means the shear strains are not equal to 0. And then we can basically plug that in into the equations that we have derived. So we still have partial w over partial x, but now we can plug in du dz. So we just take the derivative with z, so we get ky, and for the shear strain in yz, we plug in dv dz, so we get a negative of ky, and then we have our shear strains as a function of our partial derivatives as a function of our partial derivative of w with respect to x and y, respectively, plus ky or minus ky. So once we have our string components, we can go back and basically plug them back into our let me see, there were this was our compatibility equations, and then we can rewrite our compatibilities in this format. And the only thing what we do here, basically we see that we have basically two functions that are a function of the third power of w with respect to x squared y, and the third partial derivative of w with x and y squared, and the third partial derivative of w with x and y. So we can combine the two in red, and then combine the two in more yellow than orange, and we can derive that. We can basically rewrite that to have a different slightly format. So what we did here was we just took the partial x out of it, and we have basically partial gamma yz with respect to partial x here, and we take the second order partial of w with x y, and in this case gamma xz with respect to dy. So we just rewrite this in a slightly different manner, and those must be equal to 0 in order to maintain the compatibility equations. And what we do there is we just plug in back our relation between stress and strains, and we plug in back our relation between the Prandtl function phi with respect to tau xz and tau yz. And then what we can get, we can rewrite shear strains as follows, and we can combine that with our given function above, that we get a new compatibility equation. And if we simplify this, we just get, similar to our bar-harmonic equation, we get a third compatibility equation, or we get a compatibility equation that phi must satisfy in order for phi, the solution phi, or the form of phi, to be a valid solution to our stress equation. Let me see. I think there's a good location to stop, because else we're just going to go through it too fast. I'm going to bet this already confusing enough, but just to reiterate from the start, we're going to look at some solid bar that we have currently. We're going to say it was pure torsion, so we have no direct stresses. So that was the starting point that we started off with. So in pure torsion, we have no direct stresses, no sigma x, sigma y, sigma z, and we assumed also no tau xc. With that in mind, we took a look at the equilibrium equations, and we simplified it to basically 3 sets of equilibrium equations. And based on that, we could deduce that what the form of tau xz and tau yz can look like. And we said based on this form, it can be only a function of x and y. And the third one basically gives us a relationship between the two different functions in order to maintain all the three, in order to satisfy all the 3 stress equations simultaneously. Once we validated that, or we satisfied that, we showed that phi if we assume this form of phi, that d phi dz is equal, d phi dy is equal to tau xc, and negative d phi dx equal to tau yz, that our equilibrium equations are automatically satisfied. We had to look at our compatibility equations. From the compatibility equation, we looked at basically our strain and stresses are related. We plugged in our assumptions again, and we got like basically 6 compatibility equations, of which majority equal to 0, and tau xc and tau yz equal to basically the shear stress xc and yz over g. And based on that and a similar approach, we look at the equation that we have and we can basically conclude basic information out of it, how the function must look like and how it must behave. And by doing those and going through the assumptions that we have and the information that we have, we could basically come up with a set of compatibility equation, compatibility equation for torsion case. And we basically say that compatibility equation for torsion case is the second order derivative of phi with respect to x, and the second order derivative plus the second order derivative of phi with respect to y must be equal to a given constant of f in order to be 0. And if that's true, then the function of phi that we have chosen to be the solution of our problem satisfies both the stress equations and the compatibility equation simultaneously. And if we do that, then it means that our displacement field is a valid displacement field. If any of our conditions is not satisfied, that means that basically the displacement field is no longer continuous. So basically, in practical senses, mean you put some torsion on the bar, and you create, for example, a tear or a gap in your continuum material, and therefore it basically breaks down. It cannot handle it. So because this can only handle our basic conditions like of a torsion, of a bar and torsion, and the stresses being within certain limit that doesn't cause like any cracks or something like that. So that's what we discussed very quickly today. Apologize for not having markers with me. Went through it pretty fast. I will go through this again, hopefully in the next lecture, and then we'll basically start off by looking at how the boundary conditions play a role, and we will do an example or two. And then later on, we're gonna deduce the equation that we get from torsions of solid bars, and how we can apply it to a torsion of a thin wall cross section that we will use more often than a solid bar in our problems. But this will form the basis of the derivations for that. Okay, any questions? No? Okay, thank you very much, and we will see each other on Wednesday.